Okay, spinors and twistors. So a lot of what you've been presented with over the past few years has primarily been focused on just understanding spinors, and that's all fine and good, but what I want to do here is place things in a broader context and talk about twistors as well. Twistors are strange and interesting objects, and broadly speaking, we can sort of think of them as the human equivalent to our own shadows. 3D humans projected onto a 2D plane is just a shadow, just as a twistor projected onto spacetime is a null 2-plane. We are going to define this later, but let's go ahead and get started with the basics to get this stuff out of the way. From a bird's eye view, twistor theory is an attempt to unify the laws of quantum physics and general relativity by proposing that what we observe in the universe is a projection of something called a twistor. Other attempts at doing this include Eric Weinstein's famous theory of geometric unity, in which he proposes something called a Cheob operator, or a ship-in-a-bottle operator, which is something that operates on a higher dimensional space to get us everything that we observe in the universe. This is manifestly different than what previous theories have tried to do, which is to propose that everything is built on the quantum and that truly fundamental objects are quantum objects. Quantum field theory has been the successful attempt of getting quantum physics and special relativity to work with each other. But general relativity, which is the world of smooth manifolds and large, slow-moving objects, has yet to be reconciled with the two, and this is where these theories are going to come into play. Okay, really quick, I will be publishing my notes soon, within the coming few weeks. The plan I have with these notes is to have them be interactive PDFs, much like LaTeX documents are, but some of what LaTeX has to offer is limited in terms of how I would like derivations to be displayed, and these documents are going to be constantly added and updated. So with a subscription, you'll be able to have access to all of them, and notifications on my YouTube channel will go up weekly, detailing all the things that were added and changed within that week. Furthermore, I've decided that I'm going to make this a collaborative effort. So for a slightly larger subscription, you'll be able to also be co-author in these notes. You'll be able to check typos and offer insight and even provide content. Your name will go in the notes along with your expertise, and anything that I publish on YouTube that mentions your work will also go noticed. All you need to do is really just send me your work, send me a couple of derivations, make it look clear, and it'll get published and you'll become a co-author. I'm going to be doing all the heavy lifting, putting the equations in, making the derivations look nice and so forth. And so along with this, will also be released a set of community guidelines. The reason I'm doing this and adding a steep price to this is because I want to weed out all the bad actors. These are all the people who have poor intent or just aim on criticizing everything. And I kind of want to minimize this. I want this to be a healthy environment where people can collaborate together and we can make something like a great PDF out of everyone's collaborative effort. And so I'm currently working on them, and I'm making an online store for them as well, and more will be presented on this later. So with that all said, let's continue with the actual content of spinors and twistors. Okay, so we're going to go through spinors, but we're also going to be going through Lorentz transformations, where we want to understand tensors to some degree. We want to understand scalars and vectors and covectors. We want to understand Hopf vibration. There's going to be a lot of stuff to get into, but nonetheless, this is going to be a comprehensive and perhaps long, but very interesting series on getting at what twistors really are and hopefully getting at a deeper and more fundamental understanding of the universe. This is going to be a multi-part series on not just spinors and twistors, but quantum field theory in general also. And throughout this series, we are going to venture into some more abstract attempts to unify gravity with quantum forces, such as electromagnetism and so much more. So let's go ahead and start with scalars and vectors, because these, I think, are the easiest things to understand. Temperature and density, for example, are scalar-valued things. This means that all you need is a single number to measure them at any given point in space and time. The temperature in the room I'm in, for example, is 73 degrees Celsius. Or the density of molecules in my cup is 2 million molecules per cubic centimeter. I don't know, I just sort of grabbed that number out of my head, but that's the point. The point here is that all we need is just a single number to identify a system in this way. But there are other types of objects that we need to consider, such as vectors. Vectors, on the other hand, are multi-component objects, and they describe things like the flow of a river or the gust of wind. Throw a small stick into a stream, for example, establish a coordinate basis, and the motion of the stick can be completely described by these two components. Toss some light object into a windstorm, and you can use three components to measure the motion of the object in 3D space also. Okay, so these are scalars and vectors, and these are all fine and good. They're very real and tangible objects that we can measure, and we often do measure in the lab. But what about tensors? Well, a tensor can be thought of as a combination of vectors. And here I've illustrated an example of the Kerr-Newman metric, which is a metric that describes the bending of space and time around a charged rotating black hole. And here I've just decided to take the trace of the metric and map the trace, or the value of the trace, onto this 3D volume. Tensors are multi-component objects, but they don't contain the typical information that vectors will give you. Tensors are great for comparing two vectors, and they transform in very unique and interesting ways. And I don't really want to get into tensor calculus here because this is the topic of a separate playlist on tensor calculus. It's a big and vast topic, and so we want to keep this playlist relatively contained. But tensor calculus is required to at least be comfortable with spinors and twistors. And so we'll get into a little bit of tensors, but not too deep into the weeds here on this topic. So fundamentally, we need to constrain these abstractions to reality. So to do this, we need to understand how these objects transform. We don't really care about what they are per se. We care more about how they transform under something called the Lorentz transformation. So we need to talk about Lorentz transformations. So in special relativity, we find that energy and momentum are intrinsically two sides of one coin. This is because we invent something called spacetime, which is essentially a way of combining space and time together into one mathematical object. So instead of existing at a point in space and existing at a point in time, you exist at an event in space-time. Everyone and everything now has a world line attributed to their history. As you travel in space, the world line bends. If you stand still relative to another reference frame, then your world line is just a vertical line. And this is what space-time is. This is how we can think of space-time. I think that it's worth mentioning that when we study string theory, strings sweep out a world sheet. This means that at any moment in time, they exist at multiple points in space. This is going to represent the ambiguity or the uncertainty in the position of a particle that the string is representing. More on this later. So another thing that I feel obliged to mention here before we get started are my sources. Since we're going to be going through twistors, I found Huggett's book to be quite good on the topic. This is an introduction to twistor theory. But I feel like Huggett assumes a few things, and that I feel like he assumes that the reader is relatively well familiarized with tensors and spinors already. And so I don't want to make this assumption, and so we're going to cover spinors in some depth. I find the paper titled here also The Mathematics of the Standard Model by Zhao Wang to be good on the topic also, and The Physics from Symmetry to explain a few things quite nicely as well. I would also recommend Eigenkris and Richard Behiel, if I'm pronouncing his last name correctly, as good sources to get started, but we're going to go deeper into spinors because we really want to understand them inside and out so that we can get a solid understanding of twistors. We are going to start off by learning about Lorentz transformations just to get a lot of the preliminary stuff out of the way. So let's learn about some Lorentz transformations. In order to get into Lorentz transformations, let's go over some very basic stuff first. We aim to understand how light can keep time. We can imagine a situation in which we have a light beam traveling between two mirrors. The light is always traveling in space-time, but if we were to nudge the mirrors over just a little bit, the light begins to travel at an angle. The amount of time that it takes the light to reach one mirror, therefore, is lengthened. This is called time dilation, and this is just a little bit of special relativity that we're going to go into for right now. We're not going to do a full-on course on special relativity. We can do a simple derivation, which will tell us how much the time is lengthened. We start off by identifying the length by which the light beam travels between the two mirrors when they are moved. And through just some basic Pythagorean formula stuff, we can get a total distance that the light travels. Continuing with this derivation, we get that the amount of time that the moving mirror experiences is just the amount of time that passes if we were to not have moved it, divided by this factor that we call gamma, and inside gamma we define something called beta. These gamma and beta variables are extremely important in special relativity. Okay, so what does all of this mean? So a transformation in spacetime is the Lorentz transformation. This means that a transformation not only changes where you are in space, but it also changes where you are in time. And in this process, it preserves something called the metric tensor, something that we'll get into later. Let's look at some concrete mathematics to understand this first. We're going to go through an example. We can imagine, again, a particle of light bouncing between the two mirrors. If we use the standard Euclidean metric, where we just use a Pythagorean formula, we find that the total distance for a traveling light beam is not the same between two coordinate transformations. But if we were to change the metric to place the opposite sign on the spatial components of the traveling light beam, then the total distance is preserved under this transformation. This is kind of weird because it no longer looks like our nice version of the Pythagorean formula. It is for this reason that I like to call this a light distance preserving transformation. So for our light beam, our Pythagorean distance for the beam is given by the following formula. We can represent this in matrix form also, and we see that the matrix that represents this light distance is one in which spatial components have an opposite sign to the temporal ones, and all the off components are 0. This is called the Minkowski metric, and it's used to represent flat space as well. There's no need to get into curved space right now, as we're going to mostly be working in flat space. Okay, so the natural question becomes, what do these Lorentz transformations actually look like? We now know how to write a line element in spacetime, but we still haven't written down an explicit form of the transformation yet. We can stipulate that such a transformation is going to calculate the difference of the position of a point between two inertial reference frames. So always think in your mind that a Lorentz transformation requires two inertial reference frames. And think of this thing that's going to look like a matrix, or this transformation that's going to look like a matrix, as representing the transformation of a point from one reference frame to another. So we will call this an inertial frame difference transformation. I don't want to call this the Lorentz transformation yet, because I'm going at this in a unique way. We can then see that the light distance preserving transformation is the same as the inertial frame difference transformation, insofar that gamma squared is the inverse of 1 over beta squared, and we've talked about what these objects represent already. So since they are one and the same thing, then now we are going to call this a Lorentz transformation. So we are now ready to move on and discuss spinors. Well, one thing that I want to emphasize here is that spinors are actually very real things, and that their transformations can actually be represented by very real things, as we'll see. And the states by which we use to describe them are somewhat analogous to the polarization states that we see in electromagnetic waves. We could start off by considering an electromagnetic wave and just consider the y component. The electromagnetic wave is an oscillating object, and therefore we can describe it with a cosine wave, where omega is the frequency by which it travels in time, and k is the frequency by which it travels in space, and phi is just a factor by which the wave is shifted. This is all just review. More generally, we can write this with complex components as well, and when we do this, we get something called a Jones vector. This vector just tells us how the electric field oscillates in its components as time progresses. This is a simple propagation in the horizontal and vertical planes, but we shan't restrict ourselves to just three planes. We construct a vector in the complex plane as well and have it also rotated according to the following equation. It looks like this equation just came out of nowhere, but this really is just a vector in the complex plane that starts with real component 1 and its complex component is the imaginary number I. And these components will evolve in time. If we look just at the real part of the wave, we get a vector that looks like this. And we can see that in the complex plane that we also get horizontally and vertically polarized vectors. These are different than regular vectors in that they exist in the complex plane. So they're like two different types of Jones vectors, if you will. One in real space and the other in complex space, or in the complex plane. For the vector in the complex plane, we can construct different polarization states. These states are just the diagonal, anti-diagonal, left circular, and right circular polarized states, and we can animate them as well. Well, this is all fine and good, but who really cares? Well, this is where these interesting matrices come into play. We can actually rotate such polarization states into each other, and this is what birefringent crystals do. These crystals will rotate polarization states into each other and offset the plane, or offset the phase of the electromagnetic wave as well, and we can see that here in this animation. Such very physical objects can be found to be mathematically codified into such matrices. Applications of these matrices will rotate polarization states into each other. In a very abstract sense, these matrices can be thought of as moving an object about a sphere called a Poincare sphere, in which the left and right circularly polarized states are labeled antipodal to each other, and the diagonal and anti-diagonal polarization states are antipodal to each other on the sphere as well. Any point on the sphere is a polarization state that can be linearly made up of any of these other states that we've labeled on the Poincare sphere. Okay, so this is how we rotate electromagnetic waves. These matrices can physically be thought of as quite literally representing the effect of a birefringent crystal, or materials that do this sort of thing. So how does all of this relate to Lorentz transformations? Well, as it's going to turn out, we will see that rotations on the Poincare sphere are not Lorentz transformations, but rather they represent the SU2 subgroup of the Lorentz group acting on polarization states. But more on this later. We kind of want to get at this slowly. We now need to talk about electrons because up until now we've only been talking about electromagnetic waves, which are described by photons. In the case of electrons, the story is almost the same, but instead of a birefringent crystal, we use something called a Stern-Gerlach experiment, or a Stern-Gerlach apparatus. So the Stern-Gerlach experiment, conducted in 1922 by Otto Stern and Walter Gerlach, was an experiment in which electrons from silver atoms were sent through an inhomogeneous magnetic field with a constant gradient along the z-axis. We won't get into the details of this experiment, but silver atoms, they came out of the second magnetic field and they hit a screen perpendicular to their initial path. An intensity distribution is then observed on the screen, and what was observed was astonishing to say the least. When the two apparatuses are oriented in the same direction, the electrons pass through the first one, and then some are siphoned off, and electrons then pass through the second one, and what they found was a single peak. So we could say that the probability of finding this peak is 100%. Now we take the first apparatus so that it's now not oriented in the same direction as the second one. We perform the experiment again, and the result was a two-state system still. Or not still, but it was a two-state system. This is weird because you would think that the same particles, or some particles, would have been siphoned off in the first apparatus still. So what gives? Well, it seemed natural to call these two binary states, spin up and spin down, but we don't actually know if the electrons have some spin to them. But the nomenclature stuck because it was natural in the sense that things can spin either clockwise or anti-clockwise. I think it's best to just understand spin as binary degrees of freedom for the electrons. And this is really weird behavior. So how is this all gonna tie in to the concept of polarization states? Well, these two quantum states are orthogonal to each other because there's no mixing in the detector. We don't see multiple peaks on the detector. And this happens for all other orientations of the apparatuses as well. For most everything in physics, whenever we read an equation that describes a transition between two things, we are almost always reading it from right to left, not left to right. This is weird because typically we don't read things like books in this way, unfortunately, but this is how this stuck. And so we could see here all the given probabilities given the state of given the orientation of the first apparatus going to the second apparatus of a different or of the same orientation. And these are all the probabilities that we get from the experiment. And we use the idea of Born's rule to state these probabilities. Anyways, the result of the Stern-Gerlach experiment leads us to a very mathematically and interesting states that are similar to that of what we saw in the birefringent crystal. This is to say that complex numbers play a large role in transforming these objects into different states. It's just that in one case we're dealing with polarization states of photons, and in the other case we're dealing with spin states of electrons. In the case of photons, we describe such polarization transformations with the Poincare sphere, whereas in the case of electrons, we describe the spin transformations in something called the Bloch sphere. And these are all the different types of states that we can see or that we can construct given the two states that we see above in each column. Okay, let's do a little bit of math here. The matrices that orient these spin states into other spin states on the Bloch sphere are given by these matrices, which are called Pauli spin matrices, and they have some useful properties that they are traceless, Hermitian, and they square to the identity, and they anti-commute. This means that they're related to each other in the following way with the Kronecker delta, where the Kronecker delta is 1 if the indices are equal and 0 if they're not. Okay, this is all fine and good, but what gets really interesting here is that we can cast regular 3D vectors in the language of these matrices. I like to think of this as how spinors sort of see, or quote-unquote see, regular 3D vectors. Furthermore, we can look at how spinors sort of see reflections in the z-axis. Given this trend, we can infer and show that reflections along other axes are the following. So a rotation in 3D space corresponds to sandwiching our vector between two Pauli matrices of the same type. And so what about rotations in 3D space? Well, we might think that if we apply first reflection across the x-plane and then reflect again across the y-plane, the result is going to be the translated object. And what we have to do is we have to do the sandwiching because we would only get half a reflection if we don't, as we can see here. This is why using a flag to represent spinors is useful. We can see that reflecting the flag twice just results in a rotated flag, and so we can say that the spinor view of things, or in the spinor view of things, this sandwiching between two of the same type of Pauli matrices is required to properly translate and rotate vectors. Let's take a look at an animation of this in action. We can imagine that this is what such a transformation looks like. Every time the vector traverses 90 degrees in the animation, the flag has already rotated around the vector by 180 degrees. So we say that in the world of spinors, there's a double covering effect happening. Two Pauli matrices are required for rotations, and another two are required for translations. Okay, things are going to get a little bit mathy here, but we don't want to shy away from the math because math is sort of an intrinsic part of physics, if you will. But we want to generalize away from just the x and y axis and consider an arbitrary line in our plane. So the way we do this is just to use some trigonometry identities to identify the line in the plane, or the line of the plane. We're going to use theta over 2 because this is going to work out in our favor later. And what is going to end up is just going to be the original vector with the off components being applied to these exponential terms. So we just define the angle we want to translate through, and there we have it. This is what any small transition looks like from the spinner's perspective. And using Euler's identity, we say that this indeed does correspond to a rotation of our vector. And we can do the same thing for rotations around other planes. The point here is that rotations and translations of vectors are associated with a series of reflections of spinors, and it's because of this fact that spinor transformations we say double cover vector transformations. Such a fact should open our minds to the possibility that Lorentz transformations should not only apply to vectors, but also to spinors. The next question, however, will be what such transformations look like for the spinors. I like to use the language of what a spinor sees, but it might be more appropriate to use the phrase what a spinor experiences, because these are transformations. But they need to be casted in the language of complex numbers. Such matrices are unitary matrices. So the Pauli spin matrices were matrices that transition between spin states on the Bloch sphere, and now we see these new unitary matrices as sort of the lens by which vectors transform when placed in the polyformalism. Again, the polyformalism being, instead of labeling the axes x, y, and z, we label them sigma x, sigma y, and sigma z. And the transformations of such newly casted vectors then take the form of matrices formed here. And this is probably a good place to stop for this episode because I don't want to overwhelm you with too much information all at once. I'm going to leave you with this thought, though. We now have that these unitary matrices double cover regular vector spaces. This means that such a vector placed in the context of unitary matrices needs to be sandwiched between two Pauli matrices in order to transform in this space. And that these transformations we found were the same thing as transforming vectors in regular 3D space. What should we do now in order to accommodate for 4D space-time, where we now include time in the mix? This is where we're going to get into the concept of Weyl spinors. The objects that we're dealing with right now are just Pauli spinors. These things don't have the time component implemented into their formalism. And so within the next few videos, we're going to start talking about Weyl spinors and Dirac spinors and Majorana spinors, and then we're going to really dive into twistors. So with that being said, I hope you like this kind of content. Make sure to hit that like and subscribe, and I will see you guys in the next video. Bye.